And some of this I'm working with a visiting student, Pippa Kroll. All right. So this was about the spectral distortions. Now CMB anisotropies are also can be seen as a, can act as a direct detection experiment. And the basic physical effect, instead of heat exchange, is momentum exchange. So again, if you have dark matter which elastically scatters with any member of the photon baryon plasma, it will exchange momentum with it. And these oscillations of these sound waves in the early universe will be slightly affected by this exchange of momentum with this cold dark matter particle. Several people have worked on this, including locally Cory Dvorkin and collaborators. Unfortunately, Cory is not here, I think he did. And so, as a result of this, the other group that has set recent constraints is Kimberly, Buddy, and Vera Vlucevic. You can set some upper limits on how strongly the dark matter can scatter with, in this case, protons, as a function of dark matter mass. Now, this is all perfectly fine to set upper limits. But one thing that is built in and has never been discussed in all of these analyses is that they all assume that the dark matter is a perfect, ideal thermal fluid, i.e. its velocity is given just by the Maxwell-Boltzmann velocity distribution. And then what you actually solve are fluid equations for how, so you write down the momentum equation in terms of the change of the mean velocity of the dark matter and the temperature of the dark matter, and then you fold this into a CMB Boltzmann code, and then you get the limits. Now this assumption is only true either if the dark matter is tightly coupled to some thermal fluid, or if it efficiently self-interacts. And so if you efficiently self-interact, some famous guy in 1871, Boltzmann, told us that it maximizes entropy and you will get a Maxwell-Boltzmann distribution. But otherwise, there's no reason to have a Maxwell-Boltzmann distribution. So why is it important? So if you just set upper limits, you will get your upper limits wrong by factors of 2 or so. It doesn't really matter. But if we have some optimism, so CMB stage 4 will be able to probe dark matter interactions, which are up to 30 times weaker than the current upper limit from Planck. So hopefully it might detect something, or at least we should be prepared for it to detect something rather than just set some upper limit. And so then in the event of a detection of something that is consistent with dark matter scattering with baryons or photons or whatever, it would be very useful and interesting to be able to probe more properties of the dark matter. For example, how strongly does it interact with itself? And to do so, you need a formalism which is more general than just treating it as an ideal thermal fluid. So to summarize the 130 equations of this paper in 2, I've just replaced these fluid equations by just the Boltzmann equation, the collisional Boltzmann equation, solving for the dark matter phase space density, where you have some collision operator. You can write down this full collision operator in all generality, but this becomes some quite horrendous integral differential equation. So what I've done in this paper is to derive an approximation for this collision operator, a diffusion approximation, a Fokker-Planck operator, which most accurately approximates the exact collision operator, in the sense that it gives you the correct momentum exchange rate and heat exchange rate for a given distribution. And so just to illustrate pictorially what happens, I'm showing here, so I've only calculated so far numerically what happens in the background evolution, so for the unperturbed universe. So if you solve this Boltzmann-Fokker-Planck equation, so this is for some specific form of the cross-section, going as v to the 4th, because this is where the effect is stronger. This is as a function of v dark matter over v thermal, and this is the deviation from the Maxwell-Boltzmann distribution as time goes on, and you see that basically as the dark matter decouples from baryons, it is no longer maintaining a Maxwell-Boltzmann distribution, it just picks up some whatever order 1 distortions away from Maxwell-Boltzmann. Why this matters is that this will modify the detailed rates with which dark matter can exchange heat and momentum with baryons. For example, this is the fractional change in the heat exchange rate for different ratios of dark matter mass to baryon.
So could I ask a question
yeah.
on that? So sufficiently early in the universe, there must have been self-interactions. So it would have been
Sure, yeah.
right? And then let us say this dark matter is not interacting with anything else.
Right.
It's just
So it's called
expanding with the universe.
Yes.
Wouldn't it maintain the Maxwell distribution throughout?
That's right, but it would be very cold.
What is that distortion?
But it would be very cold.
This is from the interaction.
So
so there is interaction when you
here there
talk
are
about the distortion.
right. So here there are interactions with baryons, which are thermal, but no interactions. I assume no interactions with itself.
Okay.
So in the what you've pointed out is absolutely true. Initially, the dark matter will self-interact.
Mm-hmm.
However, the timing of when the self-interactions are relevant versus when interactions with baryons are relevant need not be simultaneous. So it could be that it stops self-interacting early on, and then it keeps interacting with
the baryons. That's
exactly.
what they are considering. Okay.
This is what is considered here.
Okay.
But so the more general point is that in principle, you have two parameters that you should have in, and those, if you're really agnostic about dark matter, are two free parameters.
But is it really two free parameters? Because if you look at the Feynman diagram, if it interacts, let's say, with photons, then you can have a loop where, a photon exchange between two dark matter particles.
Yeah.
Or you can have an electron-positron loop connecting the two dark matter.
Right.
So it must have some self-interaction
Yes.
that interacts with dark.
Absolutely. So I think
higher order.
within any specific microphysical model of dark matter, one is going to be predicted by the other. But if you're agnostic about the microphysics, that's what I mean by they're arbitrary.
See,
Yeah.
shouldn't I not expect dark matter to self-interact at those redshifts strongly, because otherwise I get, small-scale structure differences?
So if dark matter has no interactions with baryons and it self-interacts, it will get a pressure, but just like the baryon pressure on its own does nothing to the baryons. So the baryon pressure is relevant only when photons give pressure to the baryons, right? So the sound speed of baryons is much smaller than the C/√3. And if you didn't have photons, you would not see this up until the gene scale of the baryons. So the same thing would happen with the dark matter. If it self-interacts, it would have some gene scale, but it would be much, much smaller. Anyway, so this is what I've only shown here is the heat exchange for the homogeneous universe. What I'm hoping to find a victim collaborator for is to implement the perturbed Boltzmann focal Planck hierarchy into a Boltzmann code class, and to extract, to see how much one could be able to disentangle between a purely dark, like a non-self-interacting dark matter, if it interacts with baryons or not. All right. Are there any more questions on this piece before I move to primordial black holes? Yes?
So at what frequencies will the distortions be maximum? In other words, are these the ones where the CMB people are working on much lower frequencies?
So you're talking about distortions to the photon, or
The spectral distortions.
for the photons?
The spectral distortions.
Right. Yeah. Not this. Not this.
Oh, okay.
So okay, maybe I should clarify. So this is because there are lots of distortions involved. This is a distortion to the velocity distribution of dark matter, which indeed has a link to the distortions of the CMB
so
spectrum.
That is the signature one would look for, right?
Right.
So
one of the
what
signatures.
frequencies do they maximize? It's one way to make an experiment. What frequency should they?
I think. I don't have a good answer for you, but like if you take a chemical potential distortion, I mean you can just write down the Maxwell-Boltzmann, the Bose-Einstein distribution with the chemical potential, and you can figure out where it's maximized. You need to have some cutoff in the chemical potential, but it's a trade-off between how it's maximized and where your instrument is sensitive to, and where the foregrounds are. But this is, you can have no distortions in the dark matter and still have a distortion in the CMB. You can have a perfectly Maxwell-Boltzmann distribution of dark matter that exchanges heat with the photons and as a consequence distorted. All right. Let me move on to primordial black holes. Feel free to ask questions. I had 62 slides. I thought it would be too long, but I guess I'm going fine. All right. So a very brief history of primordial black holes. This is arguably, I think, maybe one of the oldest, if not the oldest, candidate for dark matter. So people often credit Novikov and Zeldovich for primordial black holes. I don't read Russian, but people who do told me that this paper does not really talk about primordial black holes. Hawking, 1971, I think very clearly states the primordial black holes in the modern context. So first, he provides a formation mechanism, which is considered, I think, the most standard formation mechanism for this non-standard dark matter. So if you have, there could be a large number of gravitationally collapsed objects above the Planck mass, which were formed as a result of fluctuations in the early universe. So as I said before, the idea is that on scales much smaller than those measured by the CMB, if the fluctuations are actually of order tens of %, they could, in principle, directly collapse to form black holes. And people actually do run numerical simulations of this process and do obtain black holes.
That was before he realized there is evaporation.
Exactly,
Evaporation
yes.
instead of
Yes.
14 grams.
Yeah, this was before the evaporation, yeah. I mean, you could still form them at 10 to the 14 grams. They would evaporate before today, yeah. And then the second part is that, of course, it's not said with the modern language, but he said that this could actually be the dark matter. So at the time in the 70s, it was already known that clusters of galaxies had some missing mass, even though it was not necessarily yet formulated as the dark matter problem. And so he pointed out that this extra density could stabilize clusters of galaxies, which otherwise appear to be unbound. So another person who was very active early on in